In this lecture, I'm going to introduce a very important theorem which lets you count the number of orbits of a permutation group. So firstly, let me just introduce the space of orbits. So it's usually denoted by G\U, and this is by definition the set consisting of all orbits of U. Now, before we proceed any further, let me make a record that if we have two elements U and V in U, then either GU equals GV or GU intersect GV is empty. Two orbits are either disjoint or coincide. And this is rather easy to show. I'll leave it as an exercise. If you've taken a course in group theory, of course, you'll know this. But if you haven't, I would encourage you to try it out. And if you can't do it, well, please ask. So here's an example. We've already encountered this permutation group earlier, which is the group generated by sigma. So the orbit of U under this group consists of the point U, because so this group, remember, it consists of identity of U, sigma, sigma squared, and so on, all powers of sigma. Of course, the distinct powers of sigma, so you go up to order sigma minus 1. So if you apply each of these elements to U, you will get U, sigma squared U, sigma whatever order. It doesn't matter, but the point is you'll get all powers of U, and this you recognize is the cycle of sigma to which U belongs. Remember, all of U breaks up into cycles for sigma, and so the orbit is just the cycle of U. Here's another example, and we will be looking at this example more closely in the future. We've also encountered it before. Let U and K be the set of all functions from N to K, and I want to think of these as necklaces. So these functions I'll call C. Necklaces with N beads and K colors is what I'm heading towards. So the way I'll represent such a function is I will write down the numbers 1 to N in a circle, and then each of them will have a certain color. So we'll have C1, C2, C3, and so on, all the way up to Cn minus 1. And we'll think of these as forming a necklace. And I'll define an element G. So this is a finite set, and I'll define G. Let's call it sigma, belonging to perm U and K. What does it do to a color? Sigma C of I. So it will take these colors and shift them, rotate them. The color of the second bead will become the color of the first bead. The color of the third bead will become the color of the second bead, and so on. So this will be the color of I minus 1 if I is from 2 to N. But for the first bead, of course, you should take the color of N if I equals 1. So you cyclically rotate this necklace, and the orbits is actually the set of equivalence classes of necklaces. That we encountered before, and the number of orbits is the number of distinct necklaces with n beads and k colors and k possible colors. You don't have to use all the colors. So you see, it's quite interesting to compute the number of orbits for a permutation group. And there's a formula for this, which is called the orbit counting theorem. This theorem is commonly known as Burnside's lemma, but that name is controversial because some people say Burnside wasn't the original discoverer of this theorem. So here's the theorem. What it says is that the number of orbits of G, so G in this theorem, the hypothesis is that G is a permutation group. This is the average over G of the number of fixed points. I should say sigma in G of the number of fixed points. Remember, this U sigma is the set of U in U such that sigma U is equal to U. The proof is actually really very simple. It just involves counting a certain set in two ways. So let n be the number of elements, number of pairs of the form sigma comma U. This is a subset of G cross U such that sigma of U is equal to U. Now I can count this set in two ways, either along sigma or along U. So if I count along sigma, what do I get? I get n is equal to sum over sigma in G, and how many U's are there for each sigma? Well, it's just U sigma. So this kind of looks like the right hand side of the orbit counting theorem. But now let's count along U. So then what we get is that n is equal to sum over U in U. And then how many sigma are there? Well, it's the number of the stabilizer of U in U. But by the orbit stabilizer theorem, we know that this is sum over U in U, cardinality of G divided by the size of the orbit of U. Okay, so what we get is the left hand side is exactly equal to the sum over, this is not U in G, this is U in U, U in U, cardinality of G divided by cardinality of the orbit. Now suppose that, let's take the decomposition of U into G orbits. So suppose U is equal to GU1 union GU2 union GUK. So this K is going to be just what we are looking for, the size, the number of G orbits. So we're just taking representatives for each orbit. Then this sum here, well, this is sum I goes from 1 to K, sum U belongs to G UI, cardinality of G divided by cardinality of GU. But the point is that if U belongs to GUI, then that means that GU is equal to GUI. So this is equal to sum I equals 1 to K summation U belongs to GUI, and this is just sorry, here there's no cardinality of G. I divided by it here, so there's only one. There's only one here. Okay, and what we have? U belongs to GUI, and then I have 1 over cardinality of GUI. But so this summand here is constant, and how many terms are there? Well, there are exactly cardinality of GUI many terms. So this is equal to sum over I equals 1 to k, cardinality of GUI divided by cardinality of GUI, which is 1, which is k. And well, so k is of course the number of G orbits in U. And this now concludes the proof of the orbit counting theorem.